Welcome to Aurora's South Dallas Terminal. Hi, I'm Chris Hermson, CEO and co-founder of Aurora. We're right here off of I-45, one of Texas's busiest logistics routes. I'm down here at Aurora Illuminated in Palmer, Texas. We're going to give you a chance to learn a little bit more about Aurora, our people, our technology, and our approach to safety. Why don't you follow me inside to learn more?
Hello, I'm Nat Buse, Vice President for Safety at Aurora. Safety work at Aurora is critical to how we develop and deploy our technology and plays a major role in how we build our company. At Aurora, safety work doesn't exist in a vacuum. We believe it is at the heart of commercializing our self-driving technology at scale. We're proud to be leading the industry when it comes to safety. Let me talk about some concrete ways in which we're doing that. Our safety case framework is our safety roadmap. It guides our work and enables us to understand if a self-driving vehicle is safe enough to drive on public roads. Our safety case framework is the first one ever to address both autonomous trucks and passenger vehicles. We are also the only AV company currently operating in our industry that has publicly shared its safety case framework. We think the safety case approach makes a lot of sense, and we encourage others to adopt this framework and use it as well. We have also built a team of experts who hail from across the world, multiple industries. These industries include self-driving, automotive companies, as well as other safety critical industries like aerospace, medicine, oil and gas, and nuclear power. In addition, Aurora has an industry-leading safety board that further supports our work. This depth and breadth of expertise ensures we are leveraging best practices from other fields and applying them to our work every day across the company. As part of our holistic approach to safety, we have also stood up a safety management system. This is really how we think about the organization managing risk across the enterprise. At Aurora, safety is a team sport, and this system allows us to create a strong safety culture where we address questions like, how do our employees feel about safety at the company? How do we measure it? How do we know the programs that we're running are effective? Finally, we believe that transparency and collaboration are key for us to deliver on the promise of self-driving. First and foremost, we need to build trust. Without this, we won't be able to affect the 40,000 people who die on our nation's roads every year. That's why we're committed to sharing our work, partnering with government officials and regulators, and educating the public. Being collaborative and transparent is a way to forge ahead on AV safety, pushing both Aurora and the entire industry forward.
I'm Drew Bagnell, co-founder and chief scientist here at Aurora. It's my pleasure to introduce the technology behind the Aurora Driver, what we call Self-Driving 2.0. In building Aurora as a company to develop safe and scalable self-driving products, we built the strongest team in the world with expertise in robotics, AI, and machine learning. That team recognized early the need to invest to be able to deliver a safe and scalable set of self-driving products. When I think about the need to invest, I think about an old anecdote that warns you should never try to build a ladder to the moon. It's very tempting for engineers because building a ladder makes a little bit of progress every day, but that technology won't get you there. Instead, you need to make an upfront investment and build a rocket that sits in the Earth for a long time before it crosses the 250,000 miles in just a few days. That story reminds us about the importance of investing heavily and early in key technologies. When I think about examples at Aurora, I think about our data-driven approach requiring very high-quality data. Aurora has always built 4D, both space and time labels, and developed an entire in-house team to ensure the highest quality of those labels. Similarly, our team recognized the importance of data to successful AI planning and decision-making solutions. It's been understood now for 2 decades that perception problems fundamentally require a machine learning or data-driven approach. Aurora realized, much earlier than others, the critical role data-driven methods need to play in decision-making as well. We focused on learning from expert driving as well as corrections. Our team has developed the state-of-the-art self-driving decision-making system based on deep learning techniques. You'll meet some of our team, and they'll outline some of the forecasting methods that form a part of those advances. As with our data approach, you'll see that while Aurora realized that trucking was the right first product for self-driving, we needed a major investment in sensing technology to make that viable. You'll hear about how that rocket was built in our story about First Light at our Sensing and Hardware Innovation Station. What you'll see at the Innovation Fair are examples of our approach to development in the work we're doing to build the Aurora Driver. We'll start with the Aurora hardware suite and how our software works on top of these sensors. We'll talk about the power and precision of our machine learning approach to perception. We'll introduce the Aurora Atlas, our mapping approach that enables delivering a safe product quickly and the innovations that make the Atlas tremendously scalable. We'll take you through our world-class forecasting system and how we're building a driver that makes good decisions by powerful machine learning techniques that reason about the actions of all the other actors on the road. You'll discover how our simulation technology is the most realistic in the industry and how this enables both training and testing the Aurora Driver in a wide variety of situations, including ones that are very rare or potentially dangerous on the road. Finally, as AI depends on both the quality and quantity of data, you'll see how we curate and leverage the massive amount of data that we use to build the Aurora Driver. Enjoy the Innovation Fair.
Speaking from my own experience, Aurora has the best team of engineers I've had the pleasure to work with. Many of us have prior experience in self-driving and have shipped some of the most advanced automotive systems on the road today. We've also architected high-performance consumer electronics and developed cutting-edge robotic systems. All of that experience really shows with how we work and how we develop our technology. We've collectively created a holistic and integrated approach to building the Aurora Driver, and that approach has allowed us to build faster and smarter. This ability to build faster and smarter is what will propel us toward meeting our goal of having autonomous trucks on the road by the end of 2023, with autonomous passenger vehicles following closely behind by the end of 2024. At Aurora, our hardware is purpose-built to meet the complexities of self-driving. High-precision, self-driving software requires carefully crafted hardware to power, synchronize, and ingest the data from dozens of high-bandwidth sensors. This requires a deep understanding of the software architecture and its dependencies, and a close collaboration between experienced hardware designers and software engineers. We've built a deeply integrated hardware team that produces high-performing, custom-built products that are designed and tested in-house.
Aurora's hardware includes a custom computer and sensor suite that's common across all of our vehicle platforms. This includes trucks, light-duty vans, and passenger cars. With our hardware and software teams working closely together, we recently released an upgrade to our computer, which is powerful and elegant and has 5 times more processing power and additional redundancy for added safety. Using our first principles approach with our deep industry experience, the team leverages best-in-industry components that satisfy the Aurora Driver needs so that we can focus on those developments that add value to the Aurora Driver. A great example of this is within our computer, with our proprietary time-sensitive network switch, or TSN for short. The TSN is the backbone of our computer and stitches together all the sensors and peripheral devices into one common hub. The TSN uses an advanced networking chip and a unique combination of high bandwidth automotive physical layers that efficiently move data between our sensors, computer, and vehicle. The TSN provides duplicate data packets, redundant pathways, and synchronizes our sensors down to the microsecond. Aurora's hardware team is uniquely skilled at product development, and our business model allows us to both focus and leverage our strong partnerships and technologies that are in this ecosystem.
At Aurora, we are not trying to put 1 or 2 prototype vehicles on the road. We are trying to make reliable hardware that can last for many years and has the capability to scale broadly. On the road, our Aurora Driver experiences harsh conditions. Our vehicles experience different temperatures with large gradients, rough roads, potholes. They experience rain. They are even pressure washed. To simulate these conditions in our labs in an accelerated way, we use vibration tables, different kinds of thermal chambers. We do liquid ingress tests because we want our hardware to thrive in these conditions. The most successful product design teams are the ones that partner strongly with reliability from the start of the design process.
When I think about these stresses that our hardware experience, it really motivates our thinking about managing thermals holistically. So we're designing a thermal management system that has liquid cooling support for our computers and some other components. And what's been really interesting lately is work we've done to bring up a system in our lab that enables us to do this testing in a really parametric and clever way to get a better understanding of how quickly can we respond to sudden sun exposure or sudden leaving from one environment like in the warehouse to outside in the heat. With this lab setup and with the design of a thermal management system, we are ensuring that our computer and other components stay within their operating limits.
Aurora's hardware development is strategic. We leverage deep in-house expertise to guide our high-impact innovations so that we can build a product that can scale with our business and deliver immense value for our customers. Leveraging learnings from working with 6 major OEMs with 8 unique vehicle platforms, the Aurora Driver is maximizing its commonality across different vehicle type while still ensuring the same level of quality and performance. Our approach enables us to scale and to accelerate the delivery of this industry-leading technology so that we can achieve Aurora's mission of delivering the benefits of self-driving technology safely, quickly, and broadly.
Hi everyone, I'm Emil Kadlik, a tech lead manager of integrated photonics here at Aurora. I'm going to take you through the evolution of LiDAR at Aurora. Come on down. So I was part of the Blackmore Sensors and Analytics group that was acquired by Aurora in August of 2019. At Blackmore, we worked on FMCW LiDAR for various applications, the coolest and most important being autonomous vehicles. At Blackmore, we made our systems tried to make them work for various different platforms. So to do that, what we did was create a compute and LiDAR engine box, connect that through a tether to our LiDAR head, which is the system here. All the guts and juice are kind of in this box here, and we optically connect and electrically connect through this tether to the head. So the light from the LiDAR system is emitted from this head and directed from the head, and it's also received in this head, then sent back down to the compute system, and that's where the magic happens. So what's unique about our system, being an FMCW LiDAR system, is that we can detect not only range, but also Doppler. And so what Doppler is the relative motion of that target that you've detected in your LiDAR system. So what you'll see in our data product is not only static points, which look white, but they might have a red or a blue tint to them, depicting if that item's moving towards you or away from you. One of the challenges you have as an independent LiDAR company is getting the specifications that are required from an autonomous driver. Lucky for us, we were acquired by Aurora back in August of 2019, and they unveiled the specifications that were going to help the Aurora driver. And that's when we come to First Light LiDAR, and this system here is the IOB. And this is great, actually, a great relief to see those specifications and design it specific to the Aurora driver. We were very fortunate that it wasn't a huge overhaul of our system. We just had to make a few changes here and there, and we're able to make a pretty good impact on the system. What you see inside of this box is mostly commercial off-the-shelf components. We do have some integrated components that sit on our receive side that we've helped develop. And that kind of segues very well into the recent acquisition of the Ars Technology Group back in January of this year. What's exciting about the Ars Technology Group is their focus on implementing FMCW LiDAR technology in silicon photonics. So, for example, you see the T4 LiDAR engine here. This little chip here enables most of the guts that you see in these discrete LiDAR engines that I showed earlier on chip. So that's only about a 2 by 4 millimeter chip right there. It's pretty exciting. You can see the potential downsizing of these systems as you put them on a chip. Now, to relate this to something you may be more familiar with in your day-to-day life is integrated circuit or a processor that you have in your phone or your computer. These processes to make silicon photonics and your standard integrated photonic look pretty similar. They're actually almost identical. The main difference you have is in an integrated circuit, what you're doing is moving electrons here and there. In a photonic integrated circuit, or silicon photonics, what you're doing is moving photons here or there in the manner that you'd like to. As you scale these systems, and you increase the volume, it's important to get away from connecting fibers and things like that, and actually manufacturing in silicon photonics or a photonic integrated circuit to help the manufacturability as well as the cost. So an example of doing that would be growing on an 8-inch wafer. So this is a silicon photonic 8-inch wafer, and you can see how many chips you potentially get out of just a single 8-inch wafer. Right, for example, you had this 1 by 4 millimeter chip, and so you're going to get a few of those on here, right? So it's really exciting, and that really pushes the volume that we'll need and cost reduction that we'll need in our LiDAR engine systems. So we've talked a little bit of our FMCW LiDAR engines here at Aurora, but let's take a look at it live. Take it away, Jim.
Thanks, Emil. Hi, I'm Jim Curry, Tech Lead Manager of the Sensor Perception Team at Aurora, and I'm here to show you Aurora's FirstLight LiDAR in action. LiDAR is a sensing technology that uses lasers to create a three-dimensional image of the world around the sensor. Autonomous vehicles use this three-dimensional image to localize and also to detect other actors that might be around the vehicle. This is essential for safe navigation. Aurora's FirstLight LiDAR technology uses a more advanced technique than most LiDAR sensors do. This technique is called FMCW. It stands for Frequency Modulated Continuous Wave. What FMC LiDAR can do that normal LiDARs can't is detect motion natively as a part of the LiDAR measurement. What this means is that we're able to immediately sense how fast other objects might be moving and even sense multiple different velocities that might be present on a single actor. This ultimately allows Aurora's perception system to very, very quickly detect objects as well as to accurately track and predict their motion throughout the world.
Hi, my name is Praveen Srinivasan, and I'm a tech lead and manager for perception and object detection at Aurora. Today I'll be talking about how the Aurora driver perceives the environment around it. Let's dive in. The Aurora driver must understand the environment around it, reason about other actors in it, determine the appropriate course of action, and execute that action in a safe way. Our perception system, powered by deep learning, provides an unparalleled understanding of the surrounding environment, allowing for precise decision-making in real-world scenarios. Let's explore how Aurora's perception system leverages the complementary capabilities of multiple sensors and combines it with deep learning to produce a rich understanding of the world around the Aurora driver. Aurora's perception system is powered by 3 task-specific deep learning modules: Sensor to Tensor, which is our detection engine, Sensor to Adjustment, which is a recurrent tracker, and Remainder Explainer, which helps explain everything else in the environment that the driver needs to care about. These are combined in an object persistence engine to provide seamless understanding to the driver. Today we're talking about one part of our perception system, Sensor to Tensor, our deep learning detection module that uses sensor fusion to learn and infer from multiple sensor modalities, creating a deep understanding of the world around the Aurora driver. Our state-of-the-art early fusion approach preserves the complementary strengths of different sensor modalities and progressively fuses them along with map information into a common view that allows us to produce high-quality detections of actors like pedestrians, vehicles, and cyclists in full 3D and at very long ranges. One challenge with sensor fusion is that different sensors have different resolutions and views of the world. Sensor to tensor progressively extracts and stores information from the different sensor views of the world and brings them into a common 3D representation we call the Euclidean tensor view. LiDAR data is projected into two views, the 3D Euclidean view and a wraparound range view. Projecting LiDAR data into two views gets the most out of the sensor's capabilities. The Euclidean view gives us precise 3D and velocity information, and the range view makes most of the azimuthal resolution and long-range capabilities of the sensor. Note the LiDAR points from the actor ahead of the truck. Radar is projected into a Euclidean view while extracting Doppler velocity information. Note the green on the vehicle ahead of us. These radar points provide us velocity information. We also combine image data from all the cameras on our vehicle. In this case, we are showing just one image for simplicity. We also leverage our existing map data to enrich our perception system's output. Here, map data is rasterized into a similar Euclidean view that matches the other Euclidean view grids. The result from just the raw data inputs is that we have complementary sensor data in three views: Euclidean view, range view, and the camera image. Each view contains valuable and unique information that will ultimately contribute to a holistic representation of the Aurora driver's surroundings. To extract that valuable information from each view, these data inputs are put through what we call a neural convolution engine. Our neural convolution engine harnesses the power of deep learning to process the incoming sensor data. Here's an animation of the neural convolution engine and how it creates an enriched view of the world around the Aurora driver. Euclidean tensor views from LiDAR, radar, and map data get stacked into a tensor that is processed by the neural convolution engine to produce intermediate Euclidean tensor view features. Similarly, range view inputs are processed by their own neural convolution engine to produce intermediate range view features. Image data inputs are fused with the range view features using a proprietary image fusion engine to produce a range view enriched by both image and LiDAR inputs. Ultimately, we want to produce detections in a Euclidean view to provide rich and detailed 3D information. We do this using a Euclidean ray scatter engine that transfers points from our range view data into the Euclidean space. Each pixel in a range view precisely corresponds to a point in 3D. Features corresponding to the pixel in the range view are traced back to their location in 3D and then placed in the appropriate cell in the Euclidean view. This process is repeated for each pixel in the range view in an instant, generating a corresponding Euclidean tensor view from range data. Ultimately, we have migrated the information captured in range view into the Euclidean view tensors that can now be fused with other Euclidean feature maps originating from the other sensor modalities. At this point, feature maps from all sensor modalities are in the Euclidean tensor view. They can now all be stacked together again and again processed by a neural convolution engine to produce high-quality 3D detections. The detections include properties of the object such as velocity, width, height, length, category, and uncertainties on position for each detection. This creates a representation of the world around us that is rich in data derived from various sensor inputs. Our deep learning detection engine allows us to accurately construct the world around our driver. Combined with our other two task-specific deep learning modules, along with an object persistence engine, we are able to seamlessly track detected actors on the road and reason about them. Thank you for your time today. We hope you enjoyed learning about how the Aurora driver perceives the environment around it.
Hi, I'm David Wilkie. I'm on the HD Maps team here at Aurora, and today we're going to be talking about mapping. Part of being a safe driver is knowing where you're going and what to expect on the way there. When planning for the path of an AV, we use custom-built navigational and machine learning tools that enable smart, reliable driving. At Aurora, we leverage high-definition maps that enable our AVs to focus computational resources on being a safe, on-road actor. Our HD map system, the Aurora Atlas, is designed to be a highly accurate, invaluable resource for our self-driving vehicles. We've built the Aurora Atlas from the ground up to eliminate the common pain points of HD mapping. Through a focus on being lightweight, cost-effective to maintain, and easy to expand and update, The Aurora Atlas is designed to help us commercialize our technology at scale. The Aurora Atlas is divided into tiles that fit together to represent larger areas. This allows us to easily update small areas of route individually, keeping map revisions lightweight and scalable, as well as avoiding having to deploy a massive, data-intensive update to the entire map every time a road detail changes. Our maps encode world geometry using AV sensor data to automatically generate static structures on our tiles, including buildings, vegetation, and other objects that enable us to precisely localize our AVs to make full use of our accurate HD maps. This is not only important on highways, but is critical on surface streets and in urban areas where complex road geometries require autonomous vehicles to comprehensively understand their surroundings and precisely localize relative to them. This will be essential not only as our autonomous trucks travel from hub to hub, but also when we deploy our self-driving, ride-hailing vehicles. We also use semantic annotations, which are special tags for features on or around roads to add important elements to our tiles. Our custom-built machine learning tools automatically add in content like road borders and lane lines that are then reviewed by human operators to ensure accuracy. This automated approach increases the speed and efficiency of map creation and updates, sidestepping the difficulty of keeping maps up to date using human operators alone. The addition of other road elements like signs and traffic lights is predominantly automated as well. By building machine learning models that detect these key features in our maps, we can streamline both map creation and map change detection. This approach is innovative and enables rapid expansion of the Aurora Atlas. It also makes our maps highly adaptable, and we're building towards even faster, more efficient map revisions as our machine learning tools detect and process new or changed road features. While there's a lot of valuable data in each map tile, they're structured to be lightweight and easy to update. Our map creation pipelines, tools, and machine learning models are custom built with the purpose of making expansion of our maps fast, efficient, and affordable. Like AVs themselves, the maps that drive the most value are ones that are built to scale, and that's exactly what we've developed with the Aurora Atlas. When a tile becomes outdated, whether by construction or other new road features, our online mapping and teleassist tools will ensure our AVs can continue safely on their route. We update our maps frequently using our dynamically scalable cloud-based supercomputer. This resource allows us to run large numbers of concurrent map updates, which is critical to quickly scaling the Aurora Atlas to support multiple tracking lanes. By sheer number of CPUs and GPUs, our virtual supercomputer is comparable to some of the best and fastest in the world. Thanks for learning about our HD map system with me. I now turn it over to my colleague Niels to learn about teleassist and more.
Thanks, David. Hello, I'm Niels. I lead the Remote Assist team, and I'm excited to tell you today about our online mapping and teleassist systems. We meticulously keep the Aurora Atlas up to date, but the world around us is always evolving, things like construction zones, new signage, new lane lines, and more. And as you've seen, our mapping systems are designed with the dynamic world in mind, and it's easy to swap out map tiles, but we still need to navigate these scenarios when we first encounter them. Here's how we do it. The Aurora driver constantly compares what our vehicle sees with our existing atlas. Here you can see our machine-learned detectors and classifiers in action, detecting signs and inferring virtual barriers from construction cones. These learned models help us understand where the world looks different from the Aurora Atlas. This information allows us to build an online map in real time that helps our AVs continue driving safely. When our AVs encounter complex on-road changes, we can also bring in a teleassistant to provide additional supervision and confirm the Aurora driver's decision-making. Here, the teleassist system we're designing receives an alert from our learned system about new signage. In this case, the operator proactively recommends a lane change, and the AV continues safely on its path. Because these events are very rare, a small team of teleassistants will be able to monitor an entire fleet of vehicles. After identifying areas where a tile differs from existing Atlas content, we share this data with our fleet, creating construction heat maps, deploying map revisions with surgical precision, and improving the effectiveness of our machine learning tools with each update. Thanks for joining me and learning about our work here at Aurora.
Hi, I'm Sanjaban Chaudhary, a technical lead in the motion planning team at Aurora. I work on theory and data-driven methods for imitation learning, forecasting, and decision-making. In the self-driving industry, it's common to see a diagram like this explaining how an AV makes decisions. This is the traditional cascaded approach to forecasting. First, we perceive where all the actors are, then we forecast where they'll be in the future, and finally, we make decisions based on those forecasts. While this may sound reasonable, it doesn't actually capture how the world works. Let me show you. Here's an urban example of the AV taking an unprotected left turn at an intersection with vehicles, bicyclists, and pedestrians. There's a lot going on here, so let's break it down. We can see that the Aurora driver's actions depends on what other actors in the scene are doing. We need to yield for the vehicle turning right, as well as the pedestrians crossing the intersection. Moreover, the oncoming car is also waiting on the AV to determine when it can attempt its own unprotected left. So effectively, this is a joint interaction where the forecast for this actor depends on what the AV does. Furthermore, other actors in the scene also interact with each other, and we need to take into account how those interactions could affect the AV's options. Here, the vehicle turning right is waiting for pedestrians to cross before making its turn. So our left turn depends on that car's right turn, which depends on how those pedestrians move. Driving is full of complex interactions like these. The way you behave on the road affect the way vehicles and other road actors around you behave. At Aurora, we've built our system from the ground up to reason about all of these interactions. Instead of the traditional cascaded approach, where the AV plans its movement after forecasting the movement of other actors, we take an interleaved approach to forecasting, which allows the Aurora driver to reason explicitly about its decisions in context of how other actors will respond. In complex interactions like this one, the Aurora driver reasons about the interactions among all of the actors in the vicinity. We can picture the way it works by imagining each actor as a node in a graph. The edges of this graph tell us relationships like, is actor A yielding to actor B? Looking closely at these relationships, the system can narrow things down to a subset of actors that directly affect AV's behavior. We can then abstract away the rest of the scene and only look at the graph of these relevant interactions. Our geometric transformer net inference engine, leveraging state-of-the-art graph neural networks, enables the Aurora driver to jointly reason over the graph of interactions between actor nodes trained from expert human driving data. This results in a set of self-consistent forecasts for all actors in the scene that account for the actions of the AV. By having this rich understanding of how the world may play out for different decisions, the Aurora driver is able to make more informed choices in complex scenarios like this one. Moreover, the graph structure naturally generalizes to different scenarios. Let's play this out on the original scenario. We see that by reasoning about different interactions, the Aurora driver is able to confidently navigate this complicated intersection. Our interleaved forecasting approach allows the Aurora driver to exhibit predictable human-like behavior, and the more data we collect, the better the system gets. It also ensures safe driving in potentially critical situations like the one shown here, where a cyclist pops out from behind an oncoming vehicle. The Aurora driver must quickly perceive it, incorporate it into its forecasts, and create a new plan to execute this turn safely. Okay, I've shown why this matters in urban settings, but all of this transfers to highway driving as well. Consider this common scenario on the highway where we are negotiating a merge with other actors and trying to decide how to adjust our speed to find an open slot within a stream of traffic. Here too, we apply our learned geometric transformer net inference engine. As we all know, merging is inherently an interactive process, where the behavior of other actors depends on what you do. Although it looks like there isn't room between vehicles currently, the Aurora driver explicitly reasons about potential effects of its actions on the other actors. Based on this interactive reasoning, the AV chooses to slow down, merge behind the first two vehicles, while the third vehicle makes room and merges in behind as expected. We again see how interleaved forecasting allows the Aurora driver to make better decisions in interactive scenarios, even at high speeds with an 80,000-pound truck. Learned interleaved forecasting also enables us to predict goals of other actors. We used a learned attention model to generate a matrix of probabilities for every actor on every lane. But sometimes people do unexpected things, like this actor cutting across a solid white line to merge in. Watch how the lane probabilities for this actor switch from merge lane to the AV lane as the actor cuts in. The learned attention model quickly detects that this actor is cutting in, and we slow down as needed. Even in complex scenarios, the Aurora driver is constantly computing a huge matrix of actor attentions. We saw that both urban and highway driving are full of interactions where you need to reason about how other actors will respond to your decisions. These interactions are often subtle, and hand-tuning things only get you so far. That is why we've built the Aurora driver using state-of-the-art foundational tech like the geometric transformer net, trained from expert human driver data to reason about interactions and exhibit human-like, predictable, and interpretable behavior on the road. Thank you for your time. We hope you enjoyed learning about forecasting and decision-making at Aurora.
Hi, I'm Jessie Smith. I'm a tech lead on the simulation team at Aurora, and today I'll be walking through our approach to simulation at Aurora. The reason simulation is so important to Aurora is because we believe it is the best way to fully understand how the Aurora driver is progressing. Consider the number and variety of experiences that a vehicle can have on the road. It's vast. If you want to understand the implications of a single change in the Aurora driver's code over all these experiences, you would need, we estimate, a 100 vehicle fleet operating 10 hours a day, every day for 50 years. And we change our code on our main branch more than 200 times a day. At Aurora, every code change is run through a huge number of offline tests, including simulations and perception scenarios that recreate all the experiences that are most relevant to that change, giving us fast feedback on how that change modifies performance. Around 5 million simulations are run at Aurora every day. Naturally, this requires incredibly powerful and reliable cloud computing infrastructure. Aurora's cloud infra enables developers without backgrounds in high-performance computing or distributed systems to dynamically scale simulation workloads across thousands of compute nodes. So the number of simulations we run is accelerating, see the curve, as we build more scenarios and hire more engineers, commissioning more sims. We have run over 1 billion simulations in the last 2 years, and over the life of Aurora, we calculate that at least 6 billion miles of driving would have been required to expose the Aurora driver to the same number of experiences that we have given it in sim. We also need our software stack to be architected in a robust way that supports repeatable behavior in simulation. Our simulation tools are deeply integrated with the Aurora driver software stack that runs on the vehicle. If you think of the Aurora driver as approximately broken up into the subcomponents you've learned about today, sensors, perception, planning, maps, then in simulation, we run these same software modules unmodified. We can choose to test them all end to end or take certain modules out and replace them with a synthesized version, helping us to test, for example, motion planning in isolation. Some of our more common sim configurations are shown here. This flexible architecture allows us to use our simulator to test and train the motion planning system, test and train the perception system, prototype and configure our sensor hardware, and test our maps. To give you a flavor of what this looks like, we are going to dive deeper into one specific configuration where we simulate the sensors and help evaluate the perception system. To reliably test and train the Aurora driver's perception system in simulation, we must be able to model the sensor inputs, LiDAR, radar, and camera with very high fidelity. This is an example of Aurora's in-house sensor simulation engine in action. All of this footage was created by our sensor simulation software. What you see is the same kind of simulated camera images that the Aurora driver would see. When it comes to machine learning systems, they will pick up on all sorts of details, so we need to be very careful in constructing our virtual world to be a convincing stand-in for the real one. Notice the way the wheels spin and show true smooth motion blur. The same goes for the road surface as we cruise by. These are important details for our perception system. A blurry road surface appears very different to a machine learning system than a static one. Also, note the reflections on the sides of the vehicles. These are true reflections, not faked as you might see in other AV simulators. Reflected sensor returns, so-called multipath, are an important feature of real-world operation we recreate in a physically correct way. When we pass a truck on the side of the road, which we'll come back to in a few slides, the driver is rendered realistically. It is difficult to capture human motion well. Just consider the uncanny valley. And we don't want to test and train our driver with humans that only move like 70s sci-fi robots, because that's simply not realistic, and the Aurora driver might learn incorrect behaviors because of it. Our vehicles perceive the world through cameras, LiDAR, and radar, so our simulations of each sensor modality must be physically realistic in order for the simulated experiences to translate to the real world. Let's take a look at simulations of each of the modalities in turn. Our LiDAR simulator factors in the true beam shape of each laser firing. We can handle complex effects, such as when a beam only partially covers an object, or when half a beam hits shiny car paint and the other half hits the dark rubber of a tire. Simulating radar is very difficult because of the way that radar waves behave. So quite often radar simulators just return arbitrary points on other vehicles and ignore the rest of the environment entirely. At Aurora, our simulated radar sensors actually work the same way real radars do. They construct data cubes based on reflected radar signal and accurately capture the characteristics such as angular resolution and antenna gain patterns. On the camera side, our simulator factors in the true spectral nature of light and uses state-of-the-art path tracing and Monte Carlo integration to compute each image and produce extremely realistic renderings. Finally, our first light simulator, developed together with our in-house hardware team, is so accurate that we use it to evaluate new hardware designs before manufacturing real prototypes. Next, we will look at how we use our realistic sensor simulation to complement and expand the data we capture during on-road testing. You've probably encountered something like this while driving, a stopped car on the side of the road. This is a situation where long-range sensing is crucial for autonomous trucking. We need to recognize and act on these situations much earlier than a passenger car would need to. Every time we encounter an event like this in real-world driving, we capture it and turn it into a simulation, but not just one. We expand it into a larger set of programmatically created scenarios that are variations on the original event. In the video, we first see the on-road event that we're interested in. Then we see a side-by-side view of the automatically reconstructed simulation. And note that what we're interested in here is the event itself, not reproducing things like whether there are bushes on the side of the road or not. Finally, we see 4 variants of the same scenario, not just showing a truck parked on the shoulder, but also a passenger car, a box truck, and an SUV. And this is where the scale of simulation testing comes into play. We can generate as many permutations of this as we need to. Finally, the sensor simulations also become forever tests. While the data we have of the on-road event may become outdated if we update our sensors, this synthetic test can evolve with our sensor suite upgrades, saving us from having to redo all of the work when evaluating new sensor configurations. Having created the simulated data, it's obviously important to confirm that the machine learning-based perception system processes these simulated data in the same way that it does real data. This is what really drives the requirement for high-fidelity sim. Other AV simulators with lower fidelity will struggle with the reality gap. In this video, we see that our perception systems are able to consistently detect and track the truck on the side of the road from far out until the point where we pass it and drive on. If that truck were inaccurate in some way, if perhaps its material properties were unrealistic, it's likely, in our experience, that a machine learning model would not be able to recognize it because it doesn't resemble a real truck. But thanks to the realistic virtual worlds that we build and the physically accurate simulation that we perform, our tests can be representative of a real-world scenario. Now, beyond just testing our perception system using simulated data, we are also using our simulators to train our perception system. In this video, we see a couple of instances of what we call foreign objects and debris. These are things in the roadway that aren't road actors, but that the Aurora driver nonetheless needs to be aware of and react to. In this case, there's a limit to how much data we can expect to gather from just on-road driving. While tire shreds and sofas do show up more often than one would hope, there's an endless variety of the objects that might show up in the road, in pretty much any pose. Therefore, we can make our perception system more robust to these objects by generating endless variety in simulation and training on these synthetic data. In recent experiments, we have managed to increase the recall of our remainder explainer, the module that tracks these types of objects, by around 30%, while holding extremely high precision constant by including large sets of these types of synthetic data as seen in the video. Mature, high-fidelity simulation running at scale allows us to test and train our ML-based perception and motion planning systems reliably. It is equivalent to having a fleet of 50,000 trucks that can be deployed instantly at the touch of a button. This has many benefits, but more than anything else, it allows us to move much faster. For example, the sensor suites on the trucks outside were developed and iterated on in the lab and in simulation. Then we built almost 20,000 truck simulation scenarios before we had even completed the first real-world prototype. So the Aurora driver was developed against these scenarios and was ready for real-world testing on the first truck as soon as it was road ready. And that concludes my presentation. Thank you for joining me to learn about simulation at Aurora.
Hi, I'm Darren Akuda, and I lead the Ground Truth team at Aurora. At Ground Truth, we build the training data sets that power the machine learning models behind the Aurora driver. Today, we're going to be talking about the Aurora data engine and how we advance the Aurora driver through valuable data that drives machine learning and AI. Data is key. As we look to deploy our product commercially at scale, we need to make sure it operates naturally and safely, not just in some situations, but in all situations. The real world is a messy place. There are a variety of situations that can be encountered, such as emergency vehicles. It is critical that the Aurora driver can handle situations like the ones you see on the screen, and the key to unlocking those abilities is data. When it comes to AI and ML, you'll often hear data is key, but there's more to data than sheer quantity. Aurora has collected over 4.5 million miles of driving data since we started, and that's an incredible asset. Data is the fuel that feeds machine learning. We use it to train the Aurora driver to understand and handle the different situations that we encounter in the real world. But not all data is of equal value. The real magic lies in how we find and use the right data to solve specific challenges. Situations like the one in the previous slide are not uncommon, but thankfully for all of us, they also aren't constant. This is why it's critical that we can filter through our vast and ever-growing raw data to find and label the right diverse, interesting, and specific data to train the Aurora driver. And that's where the Aurora data engine comes in. Today, we're excited to talk to you about how we advance the Aurora driver through valuable data that drives machine learning and AI. We've built important key foundational tools that enable fast interactions and rapid innovation and advancement, enabling us to power the Aurora data engine. More specifically, the Aurora data engine is our platform for collecting, searching, labeling, and training our machine learning models in a flywheel that uses model and system performance metrics to continually improve the quality of our data sets in the most efficient and impactful way. On the screen, you can see how our data flows. This fast iteration cycle provides engineers with the information they need to rapidly advance the capabilities of the Aurora driver. We also leverage these tools to tackle the long tail of autonomy effectively. With each new capability the Aurora driver is built to handle, we can use data we've already collected to advance feature development rather than recollecting data each time. A tight feedback loop from model and system performance back to data sourcing and labeling allows us to continually improve our data sets in the most efficient and impactful way. Now, let's walk through this with a concrete example: navigating construction scenes. I'm sure you've driven through situations like this. There's a lot going on. We need to detect the cones and the barrels and the signs as early as possible so we can appropriately slow down, change lanes, and handle situations like a human would. And these aren't just isolated detections. You have to be able to reason that the line of barrels actually defines a new blockage region versus being a set of specific obstacles. When we first started encountering scenarios like this, we weren't able to handle them autonomously. In this talk, we'll show you how we leverage the Aurora data engine to unlock this capability so that the Aurora driver could handle situations like this smoothly, as you see in the video. The first step in creating these capabilities was finding the right scenes that had construction elements. Aurora collects thousands of miles of on-road driving data per day. We structure our operations in on-road testing to deliberately target the most valuable events and scenarios. But how do we find the valuable data? A process can often feel like finding a needle in a haystack. To ensure we're doing this effectively, we need tools to identify the valuable items in the stream and focus the team's time. So we collect vehicle logs, the data collected from our sensors and compute that power the Aurora driver. Logs are annotated on the road live by vehicle operators and tagged automatically when uploaded to our cloud pipelines. This combination of manual and automated tagging gives a rich set of high-quality information to draw from. Our state-of-the-art suite of log search tools enables us to quickly filter and analyze data by the many attributes, including geospatial location, time of day, and the driving scenes, scenarios, and objects present at any moment in time. This enables the team to work with surgical precision on the most valuable and relevant data to the autonomy capabilities that we are developing. For even deeper insights into our data, we need systems to process this effectively and extract the most value from it. This is uniquely challenging because of the immense scale of Aurora's dataset. Our log mining platform enables engineers to identify new events within existing logs without recollecting new data. Engineers can write simple queries rather than code to find events. This takes the complex problem of identifying overlapping capabilities and simplifies it to a single query. Once we've found the relevant scenes, the next step is to label them, converting the raw data into structured data that our model training pipeline can consume. While many companies look at labels as a commodity and outsource labeling, we are investing in in-house labeling resources as well, which gives us a strategic and competitive advantage critical to deploying safely, quickly, and broadly. We can customize our labeling tools based on our specific needs and sensors. For example, Aurora's proprietary First Light LiDAR. We can leverage our existing onboard models, as well as develop additional offline models based on our own label data to create labels more effectively and efficiently than an external vendor can. The tight integration of labeling into the Aurora data engine allows us to focus on generating the right labels that can improve our capability and performance versus just creating as many labels as possible. Again, it's not just about quantity, it's really about quality. Since the beginning of Aurora, we've been doing what we refer to as 4D labeling, which is labels of 3D LiDAR data over time. These labels are composed of volumes containing rich attributes and metadata. Over the years, we have defined and iterated on a robust labeling standard that represents the real world through a set of rules, ontology, and policies. Something that sets our latest iteration of the labeling standard apart is that it is entity-centric, meaning labels for a real-world object across all sensors, LiDAR, and camera are associated as the same object across the entire time it is visible. Many companies treat each label as an independent observation. In contrast, the entity-centric model means we have one unified ground truth for a real-world object. And as you've seen from the sensor and perception stations, that allows us to reason jointly across all sensor modalities instead of handling each of them independently. While labeling is a process primarily driven by humans, we use machine learning internally to add automation throughout the labeling process, achieving far higher quality and efficiency than possible with humans alone. One example of this is 4D to 2D label transfer, where we trained a model to automatically take a LiDAR track for an object and project it into accurate bounding boxes of the same object in the camera views. This is how we quickly and accurately create associations between observations, forming the single entity that represents the real-world object across the different sensors and time. Prior to the creation of the label transfer model, association was a time-consuming and error-prone human task, which now takes a matter of seconds and is guaranteed correct by construction. Another area where automation has shown a huge impact is in labeling moving objects over time. Rather than have humans label every individual frame within a time sequence, we use a realistic motion model that leverages acausal perception, that is, looking forward and backwards through time, to automatically set the position of an object between sparse keyframes. This is much more accurate than a simple linear interpolation, as it incorporates the actual movement of the object. As you saw in the forecasting station, velocities and accelerations in our labels are incredibly important for accurate actor forecasting. This is another place where we are ahead of standard labeling vendors that focus solely on where the boxes are, but not how they move. In conclusion, as you saw today, when you've collected more than 4.5 million miles of driving data, identifying the valuable data can feel like finding a needle in a haystack. Intelligently finding valuable data unlocks its power. We've developed state-of-the-art tools that give us exactly what we need to do just that, vastly improving our autonomy capabilities and model performance. And we don't just stop there. As you learned about at the simulation station, we aggregate these valuable experiences into systems and databases, then use simulation to develop permutations, turning a single encounter into the equivalent of thousands. Thanks for listening to our talk. I hope you learned something about how both the quality and quantity of data are crucial to building machine learning models.
Hi, my name's David Madej. I'm the Senior Vice President in charge of Business Development here at Aurora. Welcome to Aurora Illuminated. I'd like to provide some insights into Aurora's approach to partnerships, which is centered around the development of the Aurora partnership ecosystem. Our partnership ecosystem has four main components: OEMs, ride networks, logistics services, and fleet services. As we focus on the technical development and capabilities of our Aurora driver, we rely upon the deep expertise of our partners to assist in the development and commercial deployment of our products. We've partnered with some of the best OEMs, including PACCAR, Toyota, and Volvo trucks. We partnered with Uber to launch our autonomous ride-hailing business. We are establishing logistics partners like FedEx to help define and refine our product solution and deploy commercially. Finally, we will collaborate with fleet service providers to ensure the uptime and availability of our products. Let's understand how these partners are linked together. Our partners are strategically selected to allow us to safely deploy at scale. For trucking, which is the top half of the slide, not only do our partners represent more than 50% of the US trucking market, but they've been selling trucks and services to the leading logistics companies for decades. For ride-hailing, which is the bottom half, the combination of the leading global automotive OEM plus the dominant rideshare network partner provides us a clear advantage as we leverage their scale, expertise, and deep product understanding. Let's talk more about our approach to selecting the right partners. For us, choosing partners starts with aligned values. For us and our partners, it starts with safety being the top priority. Afterwards, our partnership tenets are based on shared benefits, mutual respect, and trust. These tenets are ideally matched to Aurora's values, including our desire to win together, be reasonable, and focus. So how do we go about measuring our progress? We employ a deliberate, phased approach to partnerships to ensure longevity and success. Last year, our goal was to secure the right development partners to deliver driverless capable vehicle platforms. This year, our goals are to ensure these development programs are structured for commercial success and to identify select logistics partners to help inform and pilot our desired commercial product offering. Each year and every quarter, we set milestones to remain on path to deliver a product safely and at scale. Now let's shift to our structured partner development philosophy. Over the last several years, we've developed a common architecture for the Aurora driver and a common set of requirements for the vehicles powered by it. We validated this approach by integrating the Aurora driver with 6 major OEMs and 8 vehicle platforms. The result is the Aurora Driver Development Program. It starts with laying the foundation. Partnerships begin with an aligned set of values, purpose, and commitment. Before any development agreement is signed, we establish a common understanding of the goals and the process to get there. Then we shift to define and build. Early in the process, we align on the vehicle requirements that design and deploy the Aurora-powered vehicles. Throughout the vehicle design process, we lean heavily on our partners' understanding of their existing vehicle architecture to guide the modifications to satisfy these requirements. In the final step of this phase, we build prototypes. Then we shift to refine and pilot. When we're satisfied with the design and the performance of our prototypes, we build a handful of vehicles to test, refine, and validate the requirements through on-road testing, virtual testing, and commercial pilots. In our trucking pilots, we pull real loads in commercially representative ways to gain experience and incorporate customer feedback into the final product. Then we move to validate. With customer feedback incorporated, design modifications made, we now begin production of a larger fleet of verification vehicles that we run through a complete suite of driver and vehicle level validation tests. Meanwhile, we work closely with our platform partner to prepare for scaled production and commercial support. Finally, it's launch and expand. Once the safety case has been closed and production readiness assured, we push that big green button. Our partners start production, and Aurora turns its attention to the expansion of the Aurora driver's operational domain, rapidly unlocking new routes and geographies as we scale the product together with our customers. The output of this structured approach is a set of vehicles deeply integrated with the Aurora driver, that can be deployed safely at scale. Now let's talk about some of the highlights from our key partners. Starting with Toyota. We recently announced the completion of our first self-driving Sienna prototype intended for commercial deployment. As you can see in the top photo, a prototype integrated with the Aurora Driver hardware is in the last part of the design and build phase, ready to validate the interfaces and sensor placements, and we will begin to test on public roads later this year. Let's move to our next partner, Volvo Truck and Volvo Autonomous Solutions. Volvo selected Aurora to be their strategic partner to launch VAS's autonomous transport solution for the U.S. hub-to-hub market. Our relationship dates back several years where we built our first prototypes together. These photos represent our early design prototype off the current VNL. Our teams are actively engaged in the design and build phase, and we expect a fully integrated VNL to be tested on public roads in 2022. Now jumping over to PACCAR. PACCAR selected Aurora as its autonomous technology partner to create their autonomous vehicle platform integrated with the Aurora Driver. Like all of our partnerships, this started with a common vision and a commitment to safety and aligned objectives. While we're actively collaborating on this new platform, we also operate a fleet of current Peterbilt trucks, upfitted with the necessary redundancies to ensure safe, autonomous operation. This truck fleet supports our development work, and it's also used for our commercial pilots. Let's shift to our ride network partner, Uber. With Uber, we intend to deploy autonomous vehicles driven by the Aurora Driver, like the Toyota Sienna, on the largest ride-hailing network. We will leverage Uber's deep expertise in ride-hailing to strategically deploy these vehicles in the right places to enable high uptime and short wait times. Let's close out the partner highlights with our logistics partners, which includes our carriers. We intend to deploy our product as a driver as a service. It is critical that we test, learn, refine, and integrate our service with the ultimate customers. To deliver a superior service, we intend to roll out multiple pilot deployments, similar to FedEx, over the coming months across the FTL, LTL, and private fleet segments as we refine our product and pilot our service. Thank you for your time today. I hope that provided a good perspective regarding our approach to partners and the Aurora partnership ecosystem.
Hi, I'm Sterling Anderson. I'm a co-founder and the Chief Product Officer here at Aurora. I'll be talking with you today about how we're bringing the Aurora Driver to market in both trucking and ride-hailing applications. We'll spend the next few minutes discussing how we're leveraging key attributes of the Aurora Driver's common core to bring it to market. This discussion will also briefly touch on the role partnerships play in our go-to-market strategy and the way that we leverage our unique access to data to inform not just the lane and market entry sequence for trucking and ride-hailing respectively, but also the driving capabilities unlock sequence and the way that we operate our vehicles in market to maximize both service levels and vehicle utilization. The Aurora Driver has been designed to transform two markets. In trucking, our driver as a service product and the suite of tools and services that accompany it are collectively known as Aurora Horizon. In application to ride-hailing, we refer to it as Aurora Connect. I'll touch briefly on the relationship between Horizon and Connect through the common core of the Aurora Driver's hardware, software, data services, and support tools, but then I'll focus the balance of the discussion on each of these product bundles in turn. Aurora Horizon and Aurora Connect are based in a common technological core. What I mean by that is that all vehicles powered by the Aurora Driver, be they passenger vehicles, light commercial vehicles, box trucks, or even heavy combination trucks, use the same hardware, software, and data services. Besides the obvious economies of scale this allows on the hardware front, it also creates for a powerful synergistic development process in which truck development, which we've initially focused on a limited set of operational domains and driving capabilities, exercises this common technological core's validation, while car-based development expands its capabilities. Each product then directly inherits advances made by the other. What this means in practice is illustrated on this slide. Aurora Horizon's first launch will happen once we've refined and validated the safety of the Aurora Driver on highways. Now, these same highways and this validation then serves as the backbone of off-highway expansion that ride-hailing pushes forward. And the nature of that expansion is that of moving from highways into airports and moving from highways into large centers of pickup, drop-off demand. For instance, hotel parks, business districts, convention centers, other things that allow for kind of significant degree of consolidation around similar locations. As the Aurora Driver then benefits from this expansion, from these capabilities that it's endowed with, our trucking product naturally inherits those capabilities and can begin to operate in warehouse to warehouse, or what's commonly known as dock to dock type settings, which further increases the capillarity and the expanse of the road network that we can serve our logistics customers on. And then finally, as we finalize the expansion of the ride-hailing product, we'll move into more dense urban environments, like city centers, and moving people to their homes. And that in turn benefits our trucking product as well, which is now able to move, for instance, between distribution centers, stores, other locations where trucks have to move, but that are incrementally more urban and require the more complex capabilities that we're developing with Aurora Connect. Our products will come to market with powerful partners who share our values and are strategically positioned in their respective industries. As it relates to strategic positioning, it's important to note that the power dynamics in the logistics and ride-hailing value chains are reversed. On the logistics front, the OEM landscape is highly consolidated, with just 4 major manufacturers serving the North American Class 8 market, while the carrier landscape is highly fragmented. Now, this situation is the opposite in the ride-hailing space, where none of the more than dozen OEMs servicing the North American market command more than 20% share, but 2 ride-hailing networks dominate the customer-facing market. So we're excited to be partnered with strong companies from across each industry that share our values, but given the power dynamics at play, we're also pleased to have secured powerful alliances in some of the industry's most consolidated segments, with 2 of the top 3 manufacturers of Class 8 trucks in North America and the single largest ride-hailing network on the continent as well. And as we bring our products to market, we expect both our OEM and our carrier partners to play significant roles, and we expect these products that we're creating with them to create substantial value for each in their respective fields. Let's take a moment to discuss Aurora Horizon, the market it's entering, the bundles it offers, and the rollout it'll follow. We'll talk first about the market through the lens of a self-driving system, and we'll focus in this discussion on the most opportune areas where Aurora Horizon can add value. To begin, and this may come as no surprise to you, the trucking market is large, it's fragmented, and it's beset with a lot of challenges, nearly all of which can be overcome with broad access to a safe, scalable, and efficient self-driving solution. Today's carriers have to deal with a tremendous driver shortage. This is expected to only get worse as the current workforce ages out. Even when a driver is found, average annual turnover for many of the largest carriers exceeds 90%. Meanwhile, insurance costs, spurred on by the roughly 500,000 large truck crashes reported in the United States each year, have led to on the order of 5% annual increases in insurance premiums. Aurora Horizon directly mitigates these challenges caused by driver shortage, insurance costs, fuel efficiency, and vehicle utilization. It does so while critically unlocking as yet untapped opportunity in vehicle utilization and speed of service by allowing operation near round-the-clock assets as opposed to the 11-hour bursts that humans are limited to. The value unlocked by this operational speed is massive, and we expect it to be game-changing for carriers who need to move goods quickly and long distances. Aurora Horizon's rollout has been designed to start in opportune segments of logistics, launching on Class 8 combination trucks and pulling dry vans and reefers, then expanding to other truck and trailer types. The value proposition of self-driving trucks further increases with length of haul, particularly when the 11-hour service threshold is exceeded. So for this reason, and to facilitate a skew toward more highway-centric routes and the complementarity of human drivers who prefer to stay local, Aurora Horizon's starting lanes will bias toward national and regional trips, with full truckload carriers, private fleets, and less than truckload carriers. Now, when we think about these segments in the logistics space, each tends to exhibit characteristics that influence the sequence of our development and rollout. For instance, FTL carriers' trips tend to skew longer, but with more endpoints. LTL carrier networks tend to be large and consolidated, but route lengths or route distances tend to be a little shorter. Finally, Private fleets offer simplified operational integration, as you need only do it with the owner of the fleet, but generally shorter and more local hauls. So each segment is opportune in its own right and brings along interesting technical and operational considerations. We expect to deploy with each. As I mentioned, we call the product we offer in the trucking logistics space Aurora Horizon. Now, Aurora Horizon consists of the Aurora Driver that operates trucks, Aurora Beacon that allows carriers and fleets to integrate with these trucks and with their existing fleet management systems, monitor and manage their dispatch, routing, health, and finally Aurora Shield that allows carriers and fleets to maximize uptime through service and maintenance, training packages, roadside assistance, and extended support. We've designed Aurora Horizon to facilitate quick integration into existing logistics networks with minimal infrastructural burden or modifications. This process, as we designed it, is fairly straightforward. A carrier or a private fleet will first buy an Aurora Driver-enabled truck from one of the OEMs that we've worked with to develop it. They'll subscribe to Aurora Horizon, and they'll get moving. Now, in nearly all cases for the first several years, we expect that the refinement of Aurora Beacon and Aurora Shield's operational interfaces with customers will happen through pre-launch pilots of the type that you've just seen us commence with FedEx. Finally, as it relates to the rollout, we've been intentional about its lane and capability sequencing. Our geographic expansion considers technical, regulatory, and commercial factors in defining the expansion path for trucks powered by our driver. The Aurora Driver's deployment starts in Texas, the largest logistics market in the United States, and then quickly expands along high-volume interstate corridors throughout the Sun Belt and then beyond. As Aurora Connect expands the Aurora Driver's operational domain beyond highway-dominant terminal-to-terminal-like operations, the network of routes offered by Aurora Horizon will expand from the interstate heavy focus that it started with into more capillary roadways. And this allows for, as I mentioned, the kind of warehouse-to-warehouse, dock-to-dock, more urban distribution center-to-store type routes. Meanwhile, we expect supported geographies, trailer and truck types, to expand as we go. Note that this expansion path shown on this slide is not intended or expected to convey serial growth. And for instance, global routes may well begin, and probably will begin, before routes in the United States are complete. I'll spend a few minutes here now on the path to market for our ride-hailing product that we call Aurora Connect. Aurora Connect's path into ride-hailing is heavily informed and powered by our unique access to Uber's data, as I was mentioning, and our strategic direction to deploy it in partnership with Uber. We'll talk in a moment about a number of ways that this data is beneficial to Aurora in our rollout sequencing. But first, if we reframe the ride-hailing market need around highways and high-speed roadways as though the backbone for a substantial fraction of ride-hailing trips, intuitively, this makes sense. Consider the last time you hailed a ride or the roadways you traversed moving from the airport to your hotel, from your hotel to a business district, and so on. Chances are you traversed fairly high-speed roads, oftentimes even highways. In fact, when we look at data from 24 major cities, we found that on average, nearly half of all trips exceeded 50 miles an hour at some point. And what that typically means is these very likely traveled on the kind of roads that would be unreachable to a self-driving system that cannot operate at speeds like this. This is a large, lucrative, and a technically unservable segment of the ride-hailing market that self-driving systems that are limited to operation below 45 or 50 miles an hour simply cannot serve and cannot enter. So I think this is a really interesting segment as an entry point for our ride-hailing product. And for many of these trips, as I was mentioning, this is a relatively short technological step from the terminal-to-terminal-like operations of our first trucking product. As we mentioned previously, the ride-hailing market is highly price elastic. So as we expand the Aurora Driver's operational domain in both trucking and ride-hailing, and thereby increase its scale and reduce the cost of its hardware, these declining costs will allow us to increase the addressable market by bringing down prices. To speak briefly of the Aurora Connect product bundle, The Aurora Driver, as packaged in Aurora Connect, is supported by a very similar suite of operational integration and uptime maximization tools. Like Aurora Horizon, managers of Aurora-powered passenger vehicle fleets will be equipped with fleet management tools like dispatch and routing, vehicle health monitoring and incident response tools, and service and maintenance, roadside assistance, and extended support packages. Aurora Connect is designed to feather into existing ride-hailing networks like Uber or Lyft. This allows us to selectively fulfill trip requests passed to us by the network as our capabilities expand, while we simultaneously maintain high service levels for network customers and high levels of utilization for Aurora-powered vehicles. What this means is if the Aurora Driver can fulfill a given ride request that comes in through the network, it will. If it can't, for whatever reason, for instance, because the rider's intended destination requires traversal of a set of roadways it hasn't yet mastered, the network simply passes that request on to a human driver who fulfills the ride. In this way, user expectations in terms of wait time, driving safety, arrival time are satisfied. SLAs are kept very, very high, and Aurora-powered vehicles can be more heavily utilized on trips their current state of development suits them for. Finally, Aurora Connect's rollout is heavily informed by our unique access to Uber's data. Like our trucking product, we consider several technological, regulatory, and commercial factors in the market selection and sequencing for our ride-hailing product. And we've got a powerful tool to do so in Uber's data. This data allows us to prioritize markets, sequence features, and operate fleets to greatest effect. Through the years, members of the team formerly working at ATG created powerful tools to mine this data. In this example, allowing us to study how trip volumes and geographic reach are expected to change as we unlock additional self-driving capabilities, and understanding what fraction of available trips or existing trips would be addressable were we to bring online certain features in certain sequences. So we're using tools like these as we plan the entry sequence of Aurora Connect product into various markets. So that's a brief glimpse into how we're approaching the market, the product, and the rollout for our trucking product, Aurora Horizon, and our ride-hailing product in Aurora Connect. We think it's the right path, and I'm confident ours is the right team with the right partnerships to execute it. Thanks for your time today. I'll look forward to sharing more with you as this plays out.